Alright, so welcome to Engineering 270 Lecture 6. There was no video 5, there was no Lecture 5, so you're not out of sync. This is Lecture 6. For Class 5 we were doing review mostly. So today we want to talk about basically things related to call and return. And we've talked about these instructions before. A call is like a go-to, except that later you can say return and your program counter will change to the instruction after the call, so it lets you go back to where you were called from. And this is typically how we implement things like subroutines that we see in higher level languages. So here's the question. You're doing some code and you say call some routine, let's just say there. And somewhere else in your code you've got a label there, and you've got some instructions you're doing, and then eventually you say return. And this is the whole instruction. It doesn't have an operand, it's just return, but somehow the PC has to know that where it should go is right here. But then later on, if you have another call to there, and then you get your return instruction, it has to know that now it should return to this location. So the question to think about is, how does the processor remember where it should return to? And you could simply copy this return address into some location, some temporary register, but that will only work if you have a single call followed by a single return. If you have nested calls, a single save register won't work. For example, this might call there, and somewhere inside here we might say call some subroutine, and over here is a subroutine, and when this says return, it needs to know that it has to come back here, but then when this says return, it has to know that it needs to come back, say here. So you may have to remember multiple locations and know which one you're supposed to return from when you see return. And the structure of this challenge is something that we call last in, first out. It's characterized by the idea that the last place that you did a call from is the first place you want to return to. So last in, first out. So the way we implement this is to use a data structure called a stack. And a stack basically has two operations, push and pop. So pushing onto a stack means I want you to remember something. And popping from a stack means tell me what it is that you asked me to remember most recently. So here's a stack operation. Let's suppose this is our stack. Okay, I want to push a pen. And now I want to push a set of headphones. And now I want to push a flash drive. I've got three things on my stack: a pen, headphones, and a flash drive. Okay, if you say pop, what you should get back is the last thing that was pushed. If you say pop, you should get back the flash drive. And if you say pop again, you should get back the headphones. And now if you say push, and you decide to push a cable, right, the next time you say pop, you don't get the pen, you get the cable. Why? Because that's the last thing that you pushed. And now if I push my flash drive, and then I push a cable, this is what my stack looks like. And now when I say pop, what am I going to get? I'm going to get the cable. And if I say pop again, I'm going to get the flash drive. And now if I say pop one more time, I'm going to get my pen. So this is also something like a first in, last out. The pen was the first thing that I pushed on the stack. It's the very last thing that I'll ever pop out of the stack. Okay, so that's the basic concept of a stack. It's what we call an abstract data type. So two special things that can happen. One, if there's nothing in the stack and I say pop, pop, tell me what's at the top of the stack. Well, there's nothing in the stack, it's empty. That's a condition called an underflow. And that should not happen under normal circumstances. The other thing that can happen is you push a pen, you push a flash drive, you push a set of headphones, you push a cable, and now I want to push another pen, but there's no space left in the stack to push one more thing. So if I try to push one more thing, I'm going to get what's called a stack overflow. Yes, it's like the website Stack Overflow. that's a condition that occurs simply when you're asking the machine to remember too much information in the stack and there's just not enough space available. So those are two exceptional conditions. Alright, that's the abstract notion of a stack. How do we implement this? Well, I'm going to go a little CSE 121 on you here. Think of the stack as an array. And think of it as an array that holds 32 things. And we have an index into this array which we call a stack pointer, which is SP, or in the PIC processor it's STKPTR. We'll just call it SP for the most part. And when you want to push something on the stack, we do the following. We set SP to SP plus 1, and then we save at that location in this array. And when we want to pop, we do a read from stack SP, and then we subtract 1 from the stack. Okay, so with that in mind, what do these stack operations look like? So here's our stack. And I'm just going to show the first few elements. And there's 32 things in the stack, so the last element is number 31. Don't worry about that too much. And our SP, our stack pointer, is initialized to 0. So let's say push a pen onto the stack. What are we going to do? Set SP to SP plus 1, and then save our pen at that location in the stack. And then we said push some headphones, so push says SP equals SP plus 1, and then save at stack SP, so here's headphones. And then we pushed a flash drive, so we said SP equals SP plus 1, and we save at stack SP, so here's a flash drive. And now if I want to pop from the stack, what do? I read from stack element SP, so the first thing I'm going to pop is the flash drive, and then I'm going to set SP to SP minus 1. So now if I say pop again, I'll read from stack 2, because SP is 2, I'll read the headphones. And then if I decide to push a cable, what am I going to do? I'm going to set, pop, okay, so read the headphones and then set SP to SP minus 1. So now if I decide to push a cable, what am I going to do? SP equals SP plus 1 is 2, and I'm going to save it stack bracket SP, so here's a cable. An important thing to note though, the flash drive is still in this array, but it's not considered part of the stack, okay, because my stack pointer is 2, that means the last thing I pushed on my stack was element 2, a cable. This is still sitting in memory, but it's not considered part of the stack. But that's an interesting thing to keep in mind. It's got interesting security implications. Alright, so this is stack pointer STKPTR in the PIC processor. And there's also a notion of top of stack, which is TOS. And top of stack is simply the thing that's at the top of the stack, the thing that's going to be popped off next. And when I'm saying top is actually down at the bottom of the page, okay? It's not a notion of how this is written, it's not a notion of the arrays. Top refers to the last thing that was pushed on the stack, okay, or where the next thing is going to be pushed. So in this case, SP is 2, the top of the stack is stack element 2, so the cable is at the top of the stack. Okay, that's an abstract view of a stack plus an implementation. Okay, this idea, increment the stack pointer and save, or read from the stack and decrement the stack pointer. Those are implementation details. So how does this relate to the PIC processor? Well, there's a direct map to the PIC processor. So stack pointer is what we're calling the stack pointer, okay, which is STKPTR. And STKPTR, that's a special function register, okay, and it's located somewhere in here, so location FFC, that's stack pointer. So you can read that, okay, it's initialized to 0, and when something gets pushed on the stack, it's incremented, when read from the stack, it's decremented. We also have access to this thing that's at the top of the stack. Now the stack itself doesn't store pens and cables and flash drives. It stores addresses in instruction memory. Okay, and we'll see why in a minute. But what it stores is basically a 20 or 21-bit wide binary number. And we can see what that number is using the special function register top of stack. But here's a problem. These special function registers, right, they're just file registers. They're 8 bits wide. But stack contains 20 bits of information. So how can we read those 20 bits when our file registers are only at 8 bits wide? So the trick is there's not one, there's not two, but there's actually 3 top of stack registers. Top of stack low, that's L. Top of stack high, that's the high part. And then top of stack upper, which is even higher than the upper part. So the way the top of stack actually looks is you've got top of stack upper, followed by top of stack high, followed by top of stack low. So you have basically 24 bits of potential information that comprises the top of stack. There is no special function register called TOS. Okay, it's broken up into 3 special function registers, low, high, and upper. So we have to put those together when we're working with a stack. Alright, well, so the stack is used anytime that you make a call, and here's how that works. So the call instruction, remember, says I want to go to some other location, but when you're done I want to come back. So when you say call some location, here's what happens. The stack pointer gets incremented. The next instruction address gets saved onto the stack. So it basically pushes the address of the next instruction, and then it says go to whatever that location is. And when you eventually say return, here's what it does. Take the stack, whatever's at the address pointed to by the stack pointer, so the top of the stack, and load that into the program counter, and then subtract 1 from the stack pointer. So this pops the top of the stack off, right? Decrements the stack pointer. But this takes the value that was pushed up here, which was the address of the next instruction, and loads that into the program counter. So after the return instruction is done, what's the next instruction executed? What's the one that the program counter is pointing to, which is the thing that was at the top of the stack, which is the thing that was the address of the instruction after the call. So we'll work through this in homework questions and get comfortable with exactly what gets pushed and popped. But this is the basic idea, and pretty much every processor has at least one stack, and it works generally like this. Now sometimes you increment the stack pointer after you save a value. Sometimes you decrement it before you read a value. Sometimes you decrement when you push and increment when you pop, but the concept is basically the same. So 2 other instructions that you should know about in the PIC processor. One is push. And push does not take any operands. What it does is it takes the address of the next instruction in memory and pushes it onto the stack. But that's all it does. So it's like a call without actually doing the go-to part. Okay, it just saves the next instruction address on the stack. And pop does the decrement of the stack pointer without changing the PC, so it's like a return without actually doing the go-to part. And these are useful if you want to just sort of do your own manipulations with the stack. Alright, so as I said, we'll have homework questions to work through those. Next lecture, what I want to talk about is something called an interrupt, and this is a totally different concept, but it uses the idea of calls and returns in the stack, so we'll be building on what we've just done.